Hello, girls. Sorry your lecture is late this week. Today we talk about 6.3, your books. It's L'Hopital rules. You know L'Hopital rules long time because it's from Calculus 2. You work with this method in Calculus 2 class. Okay, first we prove some theorem. Tell us. Let's we have two functions f and j, or j and f. Define some closed interval a b, such as f from a equal j from a, and both of equals 0. But function j x non-zero for any x from open interval a b. What does mean? Your function is not trivial equals 0. It means 0 for some point. And then we have this kind of equation. Limit your fraction if x approach to a, your fraction f over g, equal value derivative, fraction value derivative for this point g. Okay, how we prove this fact? Proving. Let's go. Fx over gx, it will be fx minus fa, gx minus ga, right? Because value your function for point A is 0. This means I'm subtract 0. It's nothing changing. Then I'm up and down divide by same x minus a. What happened? Fraction is not changing. Because we have this arithmetic rule, up and down we can divide by something same. But if we're looking for a limit, our equation, this will be exactly limit function fx. Oh, it's not equal, it's approach. Okay. Okay, I take limit. Sorry. Gx, x approach to a. But what happened? It's right part our equation. If it's x approach to a, it will be exactly f prime to the a over g prime to the a. And we prove our theorem. Then, girls, when you study yourself, it's 6.3, please looking for theorem 6. Theorem 6.3.5. And this theorem have mistake when it's writing or something. Because they tell us if you have some two function defined for some interval, and if limit jx for x approach to a equal infinity, plus or minus, it's not depend, then limit fx over gx for x approach to a equal f prime a over j prime a. But this is not enough for solving, for use L'Hopital rule. You remember we need infinity. This limit will be infinity over infinity. This means you need not only limit your function j, it will be infinity, but and limit your function f x approach to a will be plus or minus infinity. Now be careful. And proving all correct is only this kind of problem. Okay. Continue. Now we're solving couple of examples. Let's go. This example is question B from number 6. You have limit x approach to 0, x approach to 0. Your fraction will be x squared minus sine square x over x squared. X force, you see, I make mistake. X to the force. If you plug in x to 0 in your function, you have 0 over 0. Okay, this means L'Hopital rule used correctly. X approach to 0, you have 2x minus 2 sine x cosine x over 4x cubed is equal. Here is still 0 over 0 if you plug in. But because it's mean I need found more derivative, but work with product is not so comfortable. I'm rewrite this way, minus sine 2x. I don't do anything, I'm only remember trigonometric identity, 4x cubed. Okay, it will be a limit x approach to 0 and found derivative now because we inside theorem we have 0 over 0. It will be 2 minus 2 cosine 2x divided by 12x to the square. If x approach to 0, we plug in x equals 0. It's still 0 over 0. Okay, use one more time. It will be limit 4 sine 2x over 24x. X approach to 0. Still 0 over 0. And finally, we have 8 cosine 2x over 24. Finally, if you plug x equals 0, you have 8 over 24, or this mean is 1/3. You see here we use L'Hopital rules 4 times, but every time when we try use, we checking we can use or not. Okay. Solving one more example. And here, this is question number 13, and they ask us use L'Hopital rule or trigonometric identity, and found limit. Use two method. Okay, number 13. Here we have limit tangent x over secant x approach to pi over 2. If you try plugging pi over 2, you have tangent x for x approach to pi over 2 approach to infinity. It can be positive or negative, depend approach for pi over 2 left or right. And secant x have same problem. It's infinity, positive or negative, depend where's what kind of limit you have. Okay, use L'Hopital rule. We can have x equal approach to pi over 2. We have derivative tangent. This will be secant square x. Derivative secant is secant x tangent x. Simplify, and you have a limit x approach to pi over 2 sorry, it's pi over 2, believe me, secant x over tangent x. But if we're looking for function what we have tangent x over secant x. And the same, x approaches the same number, and you have secant x over tangent x. This means if this limit is k, a limit is right part is 1 over k. What situation k equal 1 over k? It's possible only if k is equal 1. This means this limit is equal 1. Okay. How we can found this limit? Use only trigonometric identity. Try solving. X approach to pi over 2 tangent x over secant x. It will be, here we need to remember our definition trigonometrical function. Tangent is will be sine x over cosine x. Secant is 1 over cosine. This means divide. This means multiplied by cosine x and divide by 1. X approach to pi over 2. Cosine cancel it. And limit sine x for x approach to pi over 2. It's 1. You see we have same result. And use different method. What is more comfortable for you? It's your choice. Okay. One more example is question 10c from your book will be 10c. This will be, we need found limit x approach to infinity 1 plus 3 over x power x. Here we have our variable in the base, our power, and in the power. If you try plugging x infinity, you have 3 over infinities will be 0. This means it's similar like 1 in infinity power. If your base is exactly 1, it will be 1 because 1 is any power is 1. But because it's not exactly 1, we need to evaluate. Okay, let's go. This is equal a. We can take it natural logarithm both sides your equation. And because logarithmic function is continuous function, we can switch order. This means natural logarithm from limit will be limit from natural logarithm. Yes, limit x approach to infinity from natural logarithm 1 plus 3 over x power x. Use logarithmic identity, and remember we need to rewrite our function inside limit like fraction. We have natural logarithm 1 plus 3 over x, 1 plus 3 over x, divided by 1 over x. Oops. Okay. Now, if x approach to infinity, 3 over x, 0, 1 plus 0, 1, natural logarithm from 1 is 0. 1 over x, 1 over infinity is 0. This means here you have 0 over 0. We, inside our theorem, we can use, and it will be a limit 1 over 1 plus 3 over x times negative 3 over x squared divided by negative 1 over x squared. X approach to infinity. If you simplify and counting, okay, first simplify. It will be 3 over 1 plus 3 over x and if you plug in x equal infinity, you have exactly 3. This means natural logarithm a is 3 and a will be e to the cube. This means we go back and our limit when we ask us, it will be a to the 3rd degree. Okay. I think we can, oops. Section 6.4. Here let's remember about Taylor's theorem and how we use Taylor's theorem. All we did before, and I think you will be correct. It's a little bit remember, refresh. Theorem. Theorem tell us, we have function from closed interval AB and function and all derivative until order n is continuous function for this interval. This means function, derivative, second derivative, and continue nth derivative. All is continue for some closed interval AB. And n plus first derivative exists for open interval AB. What does this mean? Maybe something happened in the endpoint. If x0 for some point for closed interval AB and for any x from closed interval AB exist point C from open interval AB, this means not endpoint, such as your function fx equal fx0 plus f prime from point x0 times x minus x0 plus nth order point x0 over n factorial x minus x0 n power. Oh, believe me, here is x minus x0. And plus n plus first derivative for some point C over n plus first factorial x minus x0 power n plus 1. How we prove this theorem? Proving. Build some function ft, not pt, ft, big ft, such as fx minus ft minus x minus t to f prime c minus x minus t to the power n over n factorial f nth order for t. This function depends t. You can calculate and found derivative this f big function for t, and if you did, you have it will be minus x minus t to the power n over n factorial multiplied by n plus 1 derivative for point c. If we define function g on closed interval AB like g from c equal f c minus x minus c over x minus x0 power n plus 1 f from x0. Then you can see g from x0 equal g from x and equal 0. Use Rule's theorem. It's theorem 6.2.3. Theorem 6.2.3. Exists point C between x and x0 such as g prime c equals 0 and same time is equal oh my god, I try moving, it's not work. Okay, oh yes, that's work. And equal f prime c plus n plus 1 times x minus c to the power n over x minus x0 power n plus 1 and value your function for point x0. If we're solving this equation, we have f from x0. It's exactly from c, here is n plus 1 derivative, it's mean n plus 1 factorial x minus x0 to the power n plus 1. And this means we prove our theorem. Doing some example, can we write our Taylor polynomial? This means use Taylor's theorem, write function like polynomial. Let's go. Our function fx is cube root from 1 plus x, and x0 it will be 0, and n equal 2. Okay, found first derivative. This will be 1/3 1 plus x negative 2/3. Second derivative, it will be negative 2/9 1 plus x negative 5/3 power, and third derivative it will be 10 over 27 1 plus x negative 8/3. Okay, now we're ready. Alright, our function fx, it will be 1, because value our function for x equals 0, it's 1, plus value your derivative is 1/3, this means 1/3 x minus value second derivative is will be minus 2/9 x squared over 2 factorial and remainder is will be plus 1 over 3 factorial. Value your third derivative for some point c. It will be 10 over 27 f just a moment, I don't need 10 over 27. Okay. It will be third derivative for c times x to the third, who is equal. Now we try counting. It will be 1 plus 1/3 x minus 1/9 x squared. Here we can, if you plug in c, it stay between 0 and 1, and you have plus 5 over 81, 1 plus c to the power minus 8/3 x to the third. Okay, this is a lecture was about 6.3 and 6.4. Sorry, I try finish.
It's okay.